Good afternoon.
Just within a minute, we will start with the session, sir.
Okay,
We are
sure.
doing some technical settings for recording the video. Just as we will done with it, then we will start.
Sure. Could you make me the presenter?
Yes, sir. Yes, sir. We will make you the presenter so that you can share your content.
Okay. Thanks.
अरे क्या बात है सर, क्या बात है। आपकी कार का है? नहीं दिखी मेरे को। आ ही रहे हो क्या? अरे वाह।
Good afternoon to one and all present here. We have our next speaker with us, Mr. Saurabh Barve from TCS. Sir will be delivering the lecture or session on high performance computing on cloud technology. Saurabh sir is the technical architect with the TCS HPC Center of Excellence, COE, since 2012. Prior to that, Sir was a part of Tata Computational Laboratories, TRL, where he has supported the ESA supercomputer for domestic and international HPC customers. Saurabh sir is having around 50 years of experience in Linux and HPC administration. Sir, having his interest in the area which covers scientific computing, cloud computing, infrastructure solution architecture, and many more recent adaptations in AI. Sir, I request you to start with the session, which is based on high performance computing on a cloud technology.
Thanks for the introduction. Can you just confirm that you're able to see my slide?
Yes, sir, we are able to see your presentation.
Okay. So thank you everybody for joining. Thank you for giving me the opportunity to present this session, high performance computing on cloud technology. I would request, if you are not speaking, if you could put yourself on mute. I think we can avoid problems with echo and feedback. I would like to keep the session interactive. I will not be able to look at the chat window while I'm speaking, but if you have any questions, you may interrupt me and ask me in the middle of the presentation. Okay, so my name is Saurabh Barve. I am a technical architect with the TCS High Performance Computing Center of Excellence. We are based out of Pune, and we do HPC solution design, HPC services, and HPC innovation for our multiple customers. So the agenda for today's session is to just give an introduction about high performance computing from the business as well as the technical side. Look at the HPC architecture. If you are unfamiliar with HPC or would like to understand more, I think this would be useful. We will take a look at the emerging trends in HPC and how there is a convergence of other technologies happening on the HPC infrastructure. We will look at high performance computing on cloud, and we will look at the different cloud providers, the cloud components, and the solutions. So let us look at high performance computing from a business perspective. I realize that the audience is from the field of academia. So I think this will provide a slightly new perspective to you to look at high performance computing. Uh, so if you're looking at high performance computing, it is difficult to understand the impact of high performance computing unless you see it in a business sense. So let's take a look at life sciences, a field of drug discovery, especially for pharmaceutical companies. So pharmaceutical companies invest a lot of money in discovery of new drugs, and the discovery of new drugs involves the synthesis of prototypes, testing of prototypes, and then looking at the results of that testing and reworking the prototype. Now, this is a very cost and time intensive process. Before the implementation of HPC, of high performance computing, to take an example, there is a pharma company that invested 1 billion US dollars in order to develop a new drug. The drug design cycle takes around 10 years to isolate the compounds, to identify which compounds can be taken further, and then doing the physical prototyping and the testing. And the number of compounds that need to be tested is very large. It is in the order of millions. So for this particular case study, you're looking at 10 million compounds that need to be screened. And at the end of the screening process, you end up with 3 compounds that could be identified for future use. So this is a very large investment in money as well as time. And there is a very high rate of failure that is involved. So instead of doing physical prototyping, it is much easier to use in silico or prototyping in computer simulations. So this particular company invested around 4,000 USD in a high performance computing infrastructure. And all it took them to do the simulations for in silico drug discovery is just 11 hours of computation. And within that 11 hours of computation, they were able to screen 10 million compounds and then identify the 3 compounds for future use. So it is a tremendous improvement over the traditional way of drug discovery. So this is the kind of business impact that HPC can have. Similarly, if we look at automotive manufacturing, this is another case study for a Swedish car maker called Kineseg. It manufactured a car that goes from 0 to 400 kilometers per hour in 20 seconds. And all of these structural simulations, the aerodynamics involved in the design of that car were done on a computer. So all of it was simulated. And due to the simulation, there was no need for an expensive wind tunnel prototype. It was done completely through computer simulations. Again, this speeds up the automotive design, and similar process is also used in the aerospace industry as well. So again, you see the kind of a transformative impact that high performance computing has in the real life use cases. So it is not just something that is a bunch of parallel programs that you can run on a small cluster in your lab, but this is something that is being used at a production level across all industries. So what is high performance computing in the business sense? So high performance computing is the ability to store and process a very large amount of data. So there are 3 types of challenges in data: velocity, volume, and variety. So data is being generated at a very high velocity. You have streaming data, you have data from social networks, you have data from multiple sensors, you have data from banking and financial services. There's a very large volume of data. You have petabytes of data that is being generated every week. And you also have a large variety. So you have structured data, you have unstructured data, you have text files, you have binary files, you have image files, you have videos. And high performance computing is the ability to store all of this data and to perform complex calculations on that data at very high speeds. So it is not something that you can do on your desktop or you can do on your laptop, at least not in a production sense. So you can run your MPI program on your laptop, you can run your MPI program on your desktop. But if you have to use it in a production sense, you are looking at very high volumes of data, you're looking at very large number of calculations. So for that, you need a specific infrastructure that is required to carry out your high performance computing tasks. So you look at the different domains, and this is not the complete list of domains. Life sciences, manufacturing, semiconductor, oil and gas, banking and finance, retail and CPG, which is the products group, for customer products groups. And these workloads are compute memory intensive as well as IO intensive. So you need an infrastructure that can help you perform these complex calculations in a short period of time. So like most technology trends, high performance computing started off as a US government initiative in the decade of the 60s. And then it was adopted primarily by the automotive and aerospace manufacturers for engineering and design simulations. Then the pharmaceutical companies followed. And now high performance computing is involved in every kind of industry that you can think of. All of the industries today deal with a high volume of data, and they want to process that data to derive meaningful insight. And for that, a high performance computing infrastructure is a must. So this is till the adoption of HPC till 2012. If you stretch it out to 2020, almost every imaginable industry that you see will be on that particular map. So what is the high performance computing market share? So when we talk about the business side of HPC, we have to look at the volumes of high performance computing market share. And you can see that North America is the leading investor in the high performance computing market. And right now, the high performance computing market is around 39 billion USD globally, and it is expected to grow to around 45 billion USD by 2022. And this is investment across the globe. And we looked at the various domains for high performance computing. The graph, the pie chart on the right hand side shows this split between the different domains in terms of high performance computing usage. So you can see that government and defense is still the primary user of high performance computing infrastructure. So everything from government labs that do weather modeling to government labs that look at security, that look at encryption, or that look at the enormous user data that they have to manage for the citizens. So government and defense is the primary driver of high performance computing, but all domains use HPC to some extent or the other, whether it is retail, media and entertainment, where it is used for animation, whether it is education and research, where we are driving new technologies through academia. And 97.2% of organizations, this is according to a Gartner survey, are investing in analytics, big data, and AI. And 50% of these organizations will need HPC to run these workloads. So with analytics, big data, and AI also involve the processing of very large volumes of data. And that can be done at production scale only on an HPC environment. So there is an institute called Top 500. The Top 500 Institute maintains a list of the top 10 supercomputers in the world, top 500 supercomputers in the world, I should say. And this list is updated twice in a year. And this is the latest list based from June 2020. So there are a number of interesting things if you look at the list carefully. There are different countries where you have these large high performance computing infrastructures. You have the fastest supercomputer in Japan, but the most number of supercomputers are in the United States. China is also a major player, as are European countries such as Italy and Switzerland. If you look at the total number of cores, you can see that there are up to 1 million cores that are part of these supercomputing clusters. So these large clusters have a very large number of cores. So when you think of a cluster and a cluster of systems that will run a distributed workload, you may have thought of 32 nodes or 62 nodes, 64 nodes, 128 nodes, but these are supercomputing systems that go into thousands of nodes. In addition to CPU processor cores, which may be Intel or AMD or ARM or IBM, there are also a very large number of accelerator cores. So what are these accelerator cores? These accelerator cores are generally GPUs, or FPGAs, which are field programmable gate arrays, which are used to supplement the performance that is extracted from your CPUs. So in almost all of these top 10 HPC systems in the world, you can see that there is a fairly large number of accelerator or co-processor cores. Most of these are from NVIDIA, the accelerator cores, but they can be FPGAs or custom chips as well. Now you can look at the performance of these HPC systems. You can look at the R max and the R peak, which is the maximum theoretical teraflops per second that you can extract. This is based on the processor frequency, the instruction, the width of the instruction set, as well as the number of sockets. And you can also look at the peak performance, which is when we are running a particular benchmark, what is the peak performance that you get from that particular supercomputer. As I mentioned, you can look at the number of providers for CPU chips. You have Intel, you have Power, you have Fujitsu, you have AMD. Intel, as the largest semiconductor manufacturer, of course, largest chip manufacturer, of course, leads in the top 10 systems. And the other thing that you will see is that all of these, or most of these, are Linux-based supercomputers. So in any list of the top 500 supercomputers in the world, you will see that almost about 95% of the supercomputers run a Linux-based OS. The interconnect family. So interconnect is the high bandwidth, low latency interface that is used for message passing between the compute nodes. You will see that the leading interconnect for that is InfiniBand, which implements the RDMA protocol. So you can visit the top 500 site, top500.org, and take a look around for yourself at the different implementations of supercomputers that are across the world. And there's a lot of valuable information that you can get in terms of the technology trends across the years. Now, when we talk of high performance computing, we have looked at the business side, we have looked at the large implementations in industry as well as in the supercomputing domain. But what does the HPC infrastructure look like? What is a high performance computing infrastructure? So high performance computing infrastructure is basically a clustering of nodes, a class of systems, where nearly all of the available resources are devoted to solving a single large problem for a large period of time. So there are hundreds or thousands of identical servers that form this HPC cluster. Now, these servers may run either only CPUs, or they may have a combination of CPUs, GPUs, and other co-processors or accelerators such as FPGAs. These nodes, as we call them, these are individual servers. When they are part of the HPC system, we tend to call them compute nodes. These nodes run processes in parallel. across the cores of a single chip when you have a multi-core chip, multiple chips of a server when you have multiple sockets on a single server, and multiple physical servers. So the program that is being solved is distributed across the nodes in a high performance computing cluster. Now, the many computations are carried out simultaneously. So you may have a very large job that may occupy all of the nodes in the cluster, but you may also have a number of smaller jobs which may require a fraction or only a subset of the nodes in the cluster. So you may be carrying out many computations simultaneously. The large computational task that you have is broken down into several subtasks, and each subtask is given to a particular node to execute. The communication between these subtasks is carried out over the message passing interface or the shared memory interface. And this data sharing is carried out over the high speed interconnect, which is a high bandwidth, low latency interconnect. So the reason you need this is because standard Ethernet implementations are not designed for a high bandwidth and low latency performance. That is why you need a separate interconnect, which is called InfiniBand, or you can even have other custom interconnects from other vendors. But the characteristics that they have is that they have a very high bandwidth, up to 200 Gbps, and very low latencies in nanoseconds. The storage for this HPC compute cluster is also very large. Like I mentioned earlier, high performance computing is used to process very large amounts of data, not in gigabytes, but we're talking about petabytes here. So when you have a high performance computing infrastructure, the compute nodes need simultaneous access to that data that they are processing. So you need to have a high performance parallel file system with strong concurrency features, which can handle the constant read and write commands from the processes that are running on these nodes. So you have dedicated file systems that have the interfaces that are required for the applications that are running on this high performance computing infrastructure. Again, there are several vendors that provide this parallel file systems. In terms of the storage hardware or in terms of the compute hardware, these may be off the shelf components, but the way they are designed together, they're designed to work together as a single computational unit. Yep, so there is a request to annotate the content. So, Chandresh, was there a question or did you have a comment?
No, sir. Please carry on.
Okay. So, all right. So we'll move on to the next slide. So, how is high performance computing different from other workloads? You know, what they call enterprise workloads in industry. So, high performance computing workloads are different in that they are compute centric workloads, even though they process a very large amount of data, but they are compute centric. So they are not about storing data, but they are about crunching the data, as we say, or processing the data to arrive at some output. Now, the devices that are used in enterprise workloads or high performance computing workloads are different. So you may have specific devices from vendors such as SAP or EMC or IBM for data-centric workloads, which use, say, MapReduce frameworks or a shared memory framework. For the high-performance computing infrastructure, you have different devices. So your compute clusters may be COTS components, as they are called, meaning components off the shelf. or they may be proprietary and specific to that particular workload, such as the InfiniBand interconnect or a parallel file system that requires a particular kind of storage. Similarly, the programming methods are also different. So data-centric workloads are embarrassingly parallel. So a MapReduce or the Hadoop framework can be used for these embarrassingly parallel computations. These computations can be done in memory, with servers with very large amount of memory and which load the database or which load the entire data set into memory, and the communication can take place through a shared address space. In high performance computing, the inter-process communication takes place through the message passing interface, and remote direct memory access is used to bypass the processors for inter-process communication. And there is a distributed address space across the multiple compute and storage components that are used. Data-centric workloads usually have database components such as SQL, NoSQL, MongoDB, Cassandra, and file systems such as the Hadoop file systems. But high-performance computing generally does not use databases except to maybe store metadata for certain applications. The data is stored in parallel file systems such as Lustre, Gluster, GPFS, Spectrum Scale, Ceph, OrangeFS, and other proprietary parallel file systems that may be there. There are other differences between enterprise systems and HPC systems. So if you look at it from the bottom up, from the physical environment all the way up to the application, in this particular slide, you will see the boxes that are colored in blue are the boxes that are common for both the enterprise systems as well as the HPC systems. So data-centric workloads or end-user computing can be referred to as enterprise systems, and high-performance computing systems, the specific components are colored in green. So you can look at the environment and the compute nodes that are common to both enterprise and as well as HPC. When it comes to interconnect, enterprise systems use the gigabit or 10 gigabit Ethernet. High performance computing requires InfiniBand at 100 Gbps or 200 Gbps. The operating system is the same, so you can run high performance computing system or an enterprise system on a standard flavor or distribution of Linux or even Windows. The storage hardware may be the same. So if you have a bunch of disks or if you have even a network attached storage, that may be the same. But the file system is different. So high performance computing infrastructures require specific parallel file systems, not your default NTFS or ext3 file systems, but parallel file systems that can handle IO from a very large number of clients and still ensure concurrency. The monitoring services are common across the two. The communication libraries are different. So high performance computing requires MPI and its implementation, and also OpenMP for inter-process communication. With the large number of components in terms of compute nodes that are involved, you need a job control mechanism. So you need a middleware that will provide an HPC scheduler and a resource manager, a cluster management and a monitoring tool. The compilers, math libraries, tuning, debugging software is the same. So if you have, GCC, you can use GCC on enterprise as well as HPC systems, or any kind of C, C++ or Fortran compilers you can use in both environments. The applications are different. So enterprise applications are the kind we looked at in the earlier slide, and high performance applications are one that have that are built on top of the communication libraries such as the message passing interface. So what is a typical HPC job lifecycle use case? So HPC is used by designers and people who do simulations or drug discovery. Um, and the way an HPC job is submitted is that the engineer prepares a job submission script um, with the input data, with the particular job parameters, and submits it to the HPC scheduler. There are multiple schedulers that are available in the market, open source as well as proprietary. The applications that the engineer may be running may be open source or proprietary and may require license checkouts. Then you have a selection for the compute resources. So the end user may specify that he requires 32 nodes or 128 nodes, or he requires 1,000 license tokens. Based on the requirement that is specified by the end user, the resource selection is done by the HPC scheduler. Then the job is submitted to the selected nodes. The job simulation is done, and the output is written out to the shared storage, which is denoted here at the bottom. And the end user can then go ahead and do some post processing and visualization on that data, or he can copy that data back to his or her workstation and then take a look at the output. So this is the typical job lifecycle use case. You have to just keep in mind the scale of the environment here. So there are hundreds or thousands of compute instances or compute nodes that are present here. Similarly, there may be hundreds or even thousands of users spread across multiple geographies. So, this is a very large undertaking for any organization. But given the requirement of processing the large data, that is an investment that everybody is making. So when you are designing an HPC system, what are the kind of considerations that would go into designing, let's say, the compute part of the HPC infrastructure? So the nodes that do the actual execution for the distributed job that you're trying to run. So there are two aspects that we have to look at. One is the technology, what kind of hardware, what kind of applications, what kind of environment and maintenance you have to do for that particular technology. And the other is the business side. What is the kind of performance that is required from that HPC infrastructure? What is the kind of automation that can be implemented to save human effort and improve productivity? What kind of reliability is expected from that particular high performance computing infrastructure, and what is the cost? And of course, very importantly, there are also security considerations that go into the designing of an HPC infrastructure. Similarly, this is just something that we are looking at it from the compute side. Similarly, you have to also look at it from the storage side, because like I mentioned that we're looking at petabytes of storage, and you need to process that storage data in real time. You need to archive that data for future use. So when you're designing a solution for high performance computing storage, what are the considerations that go into it? Again, there is a technology side to it and there is a business side to it. On the technology side, you have to look at the hardware, the kind of storage media that you're going to use, what kind of a RAID configuration you are going to apply, what kind of capacity do you need, what kind of data formats do you have to support, what is the performance in terms of throughput or bandwidth that you have to support for your end user applications, and what are the technologies required for backup and archival. On the business side, you have to worry about compliance. How long do you have to retain the data? What kind of compliance requests you have, compliance criteria you have to meet? What is the recovery objective? If you lose some hardware or there is some corruption in the data, how do you recover that? What is the business requirement for recovery? Then what kind of data sources do you have? Like you may be generating some data internally, you may get some data from your collaborators, and what is the cost is the cost for the hardware and what is the cost for keeping that storage system running. So these are the design considerations that go into the designing of an HPC system. So from speaking from a TCS perspective or speaking from an industry perspective, when we have a requirement from a particular customer, we have to go into the depths of the technology and the business requirements that the customer has before we come up with a solution that is appropriate for their particular needs. So before we move on to the section on emerging HPC, just like to take a pause here. We are half an hour into the presentation. So if there are any questions or if there are any comments, I can take them now. Okay, so I'm assuming that there are no comments. I'm just going to take a look at the chat window just in case somebody has entered something. Okay, so there's a question from Professor Shiv Sutar asking about green500.org. Yes, so green500.org is definitely one other site. We talked about top500.org. Top500.org is a site that looks at the top 500 supercomputers in the world. Similarly, uh, not just green500.org, but there is also an IO 500.org, which looks at the top 500 IO systems in the world. Similarly, green500.org is also another site that looks at the data centers, the top 500 data centers that have these smart solutions for data center management. So these may be data center solutions such as liquid cooled servers or liquid immersed servers or servers that have come up with or some data center infrastructures which have come up with a novel way to reduce the power utilization or improve the power efficiency of data centers. So yes, so there is definitely a list, like I said, not just top 500, but also IO 500 as well as Green 500, which tracks these leading storage as well as data center implementations. Okay. All right. So moving on to emerging HPC. So we've looked at standard or traditional high performance computing, which is utilized in the field of automotive or aerospace or life sciences, media and animation. But as you can see, the world has changed very rapidly in the last 5 or 10 years. We have social networks. We have a very large number of devices that have inbuilt sensors in them. We have the newer communication technologies such as 5G that are coming over the horizon. So, as the technology landscape is changing, HPC also is evolving. Now, the new currency is data. As they say, data is the new oil. The in organization or the government that has the most data has the most insight into the users of that particular data. A tremendous amount of data is being generated daily, whether it be through social media networks, whether it be through streaming devices, whether it be through IoT devices. And you need artificial intelligence technologies, machine learning and deep learning to make sense of the data. It is not important merely to store the data, but it is important that you get some insights into the data. So if you look at the social networks, data based on the data that is collected in user behavior, you have advertising that is targeted for particular users. You have trends or relevant suggestions that are made to you by say streaming providers like Netflix or Hotstar, or social media networks like Facebook or Twitter. And so this is crunching of the data. It is important to process that data and come up with insights in a very short period of time. So machine learning and deep learning involve both model training and model inference. So you need training data in order to train your artificial intelligence model, and then you need to do inference on the new data that is being collected. Now, model training is a very compute intensive activity, and it is something that is missing parallelization. So there are a lot of point solutions that are being designed for certain activities in the field of AI. But when you have to do AI at a production scale, so if you are a Netflix, or if you are a Twitter, or if you are an Instagram, you are doing AI modeling at production scale. And for that, you need to make sure that your AI workloads or your analytics workloads are parallelized, so that you can reduce the computation time for that. Now, when you're talking about parallelization, high performance computing systems are something that are designed for parallelization. So even for your AI or analytics workloads, you can take advantage of the inbuilt parallelization that is present in HPC systems. Similarly, there is a convergence that is happening of HPC AI and the data analytics platform. Traditionally, there are separate environments that are designed, that are built, and that are maintained for different kinds of workloads. So you may have a high performance computing cluster, you may have an Hadoop cluster, you may have a GPU cluster for your AI workloads. But setting up these different kinds of clusters and maintaining them is a very challenging task. You have to have the necessary skills, and you have to manage the complexity of the environment going forward. Similarly, there are new digital use cases such as digital twins, where you model your entire physical infrastructure in computer simulation. Then you have technologies such as 5G enabled systems. Now, these technologies require a very strong infrastructure to collect that data, store the data, and to make some meaningful output out of that. And generally, for large commercial enterprises, these all of these different workloads are now part of a single workflow. Um, just give me 1 second. I'll just take a brief pause here. Sorry about that. It's the problem with the network. So, like I mentioned, in big commercial enterprises, these workloads are now part of a single workflow. So you may be collecting a large amount of data through sensors, and then you have to run some analytics workloads, and you have to run HPC simulations, and based on the results of the simulations, you may need to do model training. It is difficult to move data from one environment to the other. So a lot of the emerging HPC trends in industry are about convergence of the three different kinds of workloads: high performance computing simulations, data analytics, as well as artificial intelligence. In terms of the business models, public clouds and private clouds are quite popular, but due to data security reasons and the data transfer speeds and volumes of data that need to be transferred, a purely public cloud model is something that is not popular in industry. So we see that there is an increasing push towards a hybrid model where certain computation is done on premises and certain computation is done on the cloud. So these are the emerging HPC technologies that we see in industry. So when we look at these three technology trends, when we look at the components and the workload characteristics of these workloads that are coming up for all large organizations. So the high performance computing infrastructure remains the same. You have storage systems that are based on storage media such as SATA, SAS, SSDs, NVMEs, persistent memories. Then you have parallel file systems such as Lustre, Spectrum Scale, BGFS, and the specialized interconnects that run at around 200 Gbps. And then you have computes that are made up of CPU, GPU, running at peta and exaflops. And then you can look at the three different industry workloads, which is the classical HPC, large scale numerical simulation, then the analytics using Hadoop or Spark or R, and AI, which involves both model training as well as model inference. Now, the compute sensitivity, the interconnect sensitivity, the IO sensitivity of all these workloads is different. However, the underlying HPC infrastructure, which is built for parallelism, is suitable for running all of these workloads on the same infrastructure. So you have to design your infrastructure, your middleware in such a way that you are able to run these workloads on a single scalable HPC infrastructure. Now, these are the workloads that we see coming up for industry customers everywhere. This is another look at the different HPC technologies. Now, if you look at in terms of hardware, there are different hardware vendors. Speaking from a TCS perspective, a large number of these vendors are our innovation partners, our solution partners. So we work with them to develop solutions for our HPC customers. We already talked about the different kinds of storage. And if you look at the entire software stack on the right, you will see that there is a variety of applications that run on top of a single HPC infrastructure. So you have the classical HPC workloads, which you can see. This is a representative list of applications. Then you have big data applications, then you have AI applications, as well as visualization applications. Then this is the containerization stack that is now being increasingly adopted in HPC as well. Then these are some of the schedulers or the resource managers. These are the deployment or provisioning tools. These are the configuration management tools and the monitoring tools. So this gives you a pictorial representation of some of the tools across the different layers of the HPC stack. So there are several, high performance computing other vendors that provide hardware solutions for on-premises HPC infrastructures. So vendors like HP and Dell and IBM, they have their hardware physical clusters that you can purchase and you can install in your labs or in your data centers, and you can have a high performance computing infrastructure on premises, as we call it. But you may have a situation where you may not have a lab of your own, or you may not have the power or the data space or the space for data center for setting up the kind of compute facilities that you require. So what do you do in that kind of a situation? Well, like I mentioned earlier, the HPC environment is something that is very complex. And over time, it becomes harder to manage because the end user requirements keep changing. You have to support multiple application versions. You have to support multiple user environments, different workloads. In such an heterogeneous environment, these clusters become inconsistent, inflexible, complex, and unstable over time. And when you have a storage system that is on premises, it may be accessible to people in your lab or in your design center, but it may not be accessible to people who are, say, working from home in this current economy, or it may not be accessible to users across the globe who are in the same organization. So these become bottlenecks when you have to collaborate with other users in your organization. And every few years or so, technology gets obsoleted. So if you go from one Intel processor version to the next processor version, then the performance of your application may improve by 5x, in which case the user may demand that you upgrade your HPC infrastructure with the new Intel processor. But that may not be financially possible, and that may also, not be technically possible if you do not have the resources. You may have a business group or a user group that may have a sudden requirement for more compute resources or more storage resources than are available in your lab. So this is very typical of pharmaceutical customers, where if they are doing drug discovery, then while they are doing drug discovery, then while they are uh, synthesizing compounds, they may have a requirement for a very large number of compute or a very large amount of storage. But when that particular phase is completed, then they just want to move that data to archive, and they may not revisit that data for another 6 months. And their compute requirement may be a tenth or a hundredth of what it was at the peak period. Now, if you provision hardware on premises for the peak capacity that your users require, what do you do with that peak capacity when that requirement is no longer there? It is just wasted hardware, and you're wasting money on power and infrastructure, and not to mention human resources and system administrators who have to keep to maintain that particular hardware. What do you do in that kind of solution? Or you may have a business group that has a time constraint. It may need a solution in a very short period of time to get the first mover advantage in a market, say, for example. What do you do in that case? You may not be able to, you may be able to provision that particular compute facility in your data center, but you may not be able to provision it in the time in the time constraint that is required by the business group. So these are the challenges in traditional on-premises HPC infrastructures that are set up in data centers. How do you resolve this? You resolve this by taking your high performance computing infrastructure to the cloud. So you may have, so this is just a summation of what we talked about in the last slide. So you may have a demand for a workload that is compute and memory intensive, that is beyond the capability of your on-premises hardware infrastructure. Your in-house infrastructure may be limited because of your financial resources or your data center space. Adding new infrastructure or adding a particular kind of technology may be prohibitively expensive for you. Adding different kinds of processing environments or storage environments will end up being difficult to manage. Some business users group may have time constraints in which to process their data. And you may also have issues in terms of collaborative access across the globe and the kind of security and data management that is required to meet compliance standards. So what do you do in that case? In that case, you go to an environment that is flexible, that is elastic. Now, elastic means not only it can scale up, but elastic is like a rubber band. When you let it go, it can also contract. So it scales up when you need it, and it scales down when you don't need it. So that is the flexibility that we talk about when we say an elastic environment. It is also scalable at a rapid pace. So the cloud provider will be able to provide you with a very large number of instances or a very large amount of storage in a very short period of time, because that is the business the cloud provider is in. With a traditional in-house model, you are paying for the data center, you are paying for electricity, you are paying for the capital expenditure of purchasing the servers, the storage, the licenses, and you are paying for the operational expenses of, again, electricity, system management, licenses, and everything. With the cloud, you get a pay-per-use model. So you only pay for what you use. So you're charged for per hour for the compute instances they use, for you use, per GB for the storage that you use, per license token for the number of licenses that you use, which may make it cheaper to run your workloads on the cloud. Now there are thresholds for this kind of saving. So there is a particular threshold, say around 40%, beyond which the cloud or under which the cloud is much cheaper than running the same thing on the in-premises data center. The cloud environment is also easy to manage in that you do not have to do any management. You merely have to set up the users and allow the users to log in and submit jobs. With the ability to scale up the infrastructure very quickly, you can process your workloads quicker, and you can get better performance on the cloud than you may get on in the infrastructure in-house. Since cloud infrastructures service a very large number of users, they are built with security in mind, because they have to comply with the security and compliance requirements of multiple customers across multiple domains and multiple geographies. They are built with security and access in mind. So the cloud environment has really taken off in the last 4 or 5 years as businesses scale up very quickly. So if you look at this chart of the cloud infrastructure services market revenue from 2016 to 2019, you will see almost a threefold jump from the Q1 of 2016 at $8 billion to $26 billion in the Q2 of 2019. That is quite a big growth rate, and it keeps growing. And the cloud market is around 100 billion USD. And the leading provider for among these cloud providers is Amazon, which has around a 33% share as of Q2 2020. Azure is fast catching up, even though it was a late entrant to the market as compared to AWS. And there are also other cloud providers such as Google and Alibaba, IBM, Salesforce, Tencent, and Oracle. These are not as big a player as Amazon or Azure. Almost all of these cloud providers provide resources for high performance computing, and we will take a look at the top 3 cloud providers according to this chart: AWS, Azure, and Google Cloud. And we'll look at the services that are provided on these 3 cloud providers. So what are the different cloud components, and what are the solutions that are offered by these cloud providers? So before we move on to this section, I'll take a pause again, and I will invite questions. I will just take a look at the chat window if you have typed something in the chat window. Okay, so there's a question here. Let me see if I've missed something earlier. Okay, there's a question from Naveen Chauhan. Any resource manager which is freely available? Yes, there are several resource managers and schedulers that are freely available. There is one called Slurm. I will just type these names here. There is one called Slurm. There is one called the um, Open Grid Scheduler, which is a spin-off from the Sun Grid engine. Then there is Torque, um, which is from Adaptive Computing. Then there is actually PBS. So Altair has a scheduler called PBS Pro. The scheduler part of this has been open source, so that is available. Anybody can download it. So there are multiple free schedulers that are available that you can set up easily in your environment, and these are openly licensed. There is one question from Sham. Can we get the video lecture URL at the end of the day? I think that is a question for Dr. Sushil. I think this session is being recorded. So I think you can get in touch with Dr. Sushil. He may have the answer to that. There's a question from Lalit. Is there any research plan area funded projects and plan for HPC? So I am not sure if you're talking about this in terms of the university or if you're talking about in terms of TCS. So within TCS, like I said, I'm part of the Center of Excellence. So we do carry out research and innovation in the field of HPC. In terms of university, so again, that is a question for Dr. Sushil. He may be able to answer that. There is a question from Naveen. Can we generate traffic from IoT devices and test some scheduler algorithms? Definitely, you can do that. So you can definitely use HPC storage systems, parallel file systems. There are also parallel file systems such as Gluster or Luster that are available for download and testing. So these are open source. You can download them, test them for your IoT data, and you can check your scheduler algorithms. Okay, there is a question. What is the difference between a DAG scheduler and resource scheduler with reference to Spark? So a resource scheduler is used to keep track of the available resources in the HPC environment. So resources are defined in terms of the compute resources that are available, in terms of the storage resources that are available, or in terms of the licenses that are available. So like I mentioned, you may have a user job that requires, say, 500 processors or that requires a few tokens. So it will keep a track of these hardware resources or these particular resources that are defined in the scheduler, and it will allocate the resources to that particular job based on the resources that are available. So you can run your Spark workloads through the HPC scheduler. So if you have a Spark workload and you desire certain computational resources, then you may specify what kind of resources you want your job to use, and the resource scheduler, the resource manager, and the scheduler will take care of that. The DAG scheduler is more in terms of finding the optimized way of scheduling your Spark job. So it will not consider what kind of hardware resources are being used, what kind of licenses are required, or what kind of compute resources, how many sockets, what kind of memory, what kind of um, parallel file system storage is required for that particular job. So it is more of a generalization of the map reduce model. So these schedulers do not. So the follow-up question is, how do these schedulers interact? So these schedulers do not interact. The um, map reduce. You can either have a map reduce job, be executed through its own schedulers such as Yarn, or you can use the HPC schedulers such as um, LSF or PBS, and you can run your workloads through that. So there is no real interaction between these two kinds of schedulers. So the HPC scheduler is more in terms of managing the requirements of the end users and matching them with the hardware or compute resources that are available in the infrastructure that you have set up. Okay, so we will move on to the HPC cloud components and solutions. So there are three main cloud service models that you will find from the different cloud service providers. The first and the most basic is the infrastructure as a cloud. So what infrastructure as a service, I would say infrastructure as a service model um, involves is making available for the end user the infrastructure that is available on the cloud. So it is just it will give you access to the processors, it will give you access to the memory, the storage, and then you can create your own environment on top of that. So when you're talking about cloud, we are talking about a virtualized environment. Um, we are talking about VMs or containers that are running on top of the infrastructure that is available at the cloud provider side. You are given access to an operating system. You can log into the operating system and you can run your application, or you can create an application on top of that. So that is the general definition of infrastructure as a service. Now, there are cloud providers that also provide a bare metal infrastructure. So instead of a VM or a container running on top of the hypervisor, you can get access to the OS that is directly installed on the server. So it is just like logging into your server in the lab directly, or logging into your workstation or your desktop. Now, this kind of a model is generally used by solution architects, which develop solutions on top of the infrastructure. So, if you want to have a banking solution or an automotive simulation solution or a drug discovery simulation solution, you can get access to the operating system, you can get access to the libraries, and you can build your own solution on top of that. The second cloud service model is the platform as a service. So the platform as a service is, let's say you build a solution on top of that on the infrastructure, and you make it available for your application developers. So you can make if you have done if you have done any coding for AI, you can have Jupyter notebooks available for your application developers, and they can simply log in and write their MLDL code into that. Or you can have microservices that are running on the cloud, and the users can make use of these microservices, and they can write their own applications. So you can have applications that say do log analytics, or you can have applications that do transaction processing, and using those applications, an application developer can build an entire solution. So that is what is known as PaaS, or platform as a service. The third one is the software as a service. So here what you have is the consumer of this is the end user. So here you have a cloud app that is ready to go, and it is delivered directly to the end user. So if you know Office 365, so that is a SaaS offering. So you can just log into office.com. You can open Microsoft Word or Microsoft PowerPoint, and you can just create your documents. So that is software as a service. So that is the highest level of cloud service model. There are, of course, other models that are coming up, but they are variations of these. So you may have container as a service, or you may have storage as a service, or you may have a network as a service. Now, though these are defined for different kind of industry segments, but again, what you are actually doing is providing either the infrastructure, the platform, or the software to build solutions on top of your cloud service model. Similarly, you can also have an HPC as a service. So you can have, a service where customers just log in, come in with their input data, submit a parallel job, and see the output. So you can have multiple solution offerings based on top of these cloud service models. So let us take a look at the three main cloud service providers that we looked at in terms of market share. The first one is Amazon, the oldest cloud service provider in the market in the public cloud. It is also the biggest, and it provides a slew of solutions for your high performance computing needs. There are a large number of compute instances, a large variety of compute instances available um, on Amazon AWS, which is the Amazon Web Services, which are known as EC2 instances, which are the Elastic Cloud Compute instances. These are available in CPU form as well as GPU form. So you can get CPU instances based on Intel processors or AMD processors. You can get GPU instances based on NVIDIA. You can also get ready-made container solutions. You can get object storage that is based on the S3 interface. You can also get, POSIX, storage with a POSIX interface that looks and behaves like NFS. You can create solutions on top of this based on any kind of scheduler that you want, whether it is Alter-P, Base Pro, IBM LSF, or Slum. You can have multiple visualization solutions. So to enable your end users to do remote visualization of the output from their simulation workloads. You can support multiple industry verticals. So, like we saw in the earlier chart, the um, application characteristics for different industry verticals are different. So you may have compute intensive workloads, IO intensive workloads, or compute and IO intensive workloads. On the basis of that, you can select your compute instances, your GPU instances, or your storage type, and you can create a solution on top of that. So AWS supports different kinds of industry verticals, and AWS has partnerships with a very large number of industries, with a number of software vendors. There also are partners in designing solutions and providing infrastructure for different kinds of customers. So this is kind of a list of the different component services that are available on AWS. So in AWS, you can have different kinds of compute instances. You can have reserved instances where you commit to using a specified number of instances on AWS. You can have redundancy across multiple geographies. So AWS has multiple data centers across the globe. So you can have virtual public clouds in AWS in different geographies. So you can have a cloud environment in North America. You can have one in Europe. You can have one in Asia, and they can all be connected to each other through the AWS internal interconnect. You can also easily move data between these different AWS cloud environments, and you can also have redundancy and replication. So you can have replication within a data center, within a particular region, within a geography, or across multiple geographies. And like we said, elasticity is a very important component of AWS, of any public cloud provider. You can expand and shrink your resource allocation. In terms of storage, AWS not only has your traditional file systems, but also high performance parallel file systems such as Lustre and Spectrum Scale GPFS. There are multiple orchestration and scheduling mechanisms that are available. You can run your own HPC scheduler, or you can use schedulers such as AWS Batch that are available by default from AWS. And there are multiple tools available for data management and security. So you can sync data between your data center and the AWS cloud. You can transfer large amounts of data using the AWS Snowball devices, where they send you a kind of a hardware device that looks like a box. You can connect it to your network, copy data onto it, and then ship that box to the AWS data center, and they copy it onto your storage instance there. The storage is elastic. It grows as per your requirement. And, there are different tiers of storage. So there's fast access storage, there's medium access storage, there's slow access storage. So you can have storage media such as NVMe, SAS disks, SATA disks, hard disks, or you can even have tape storage. On top of the compute infrastructure, AWS has also built a very wide assortment of tools for management and monitoring of the infrastructure that you set up on AWS. Was there a question? Okay, so there's a request to share my email address. So that is in the last slide of the presentation that I will display for the benefit of everybody. So this is a kind of a solution approach for designing an HPC solution on AWS cloud. You can use a similar kind of approach for designing something on Microsoft Azure or the Google Cloud. So let's say you have an HPC infrastructure on premises and you want to create an HPC infrastructure on the cloud. So how would an HPC center of excellence or how would somebody in TCS go around designing that solution for the cloud? So you have to first assess the state of the as-is infrastructure from the hardware all the way up to the application. Then you have to identify the alternatives for your existing infrastructure on AWS in terms of storage as well as compute and network. Then you have to look at what kind of tools you would require on AWS to deploy, provision your infrastructure, monitor it. Then you have to look at the access and security alternatives. So on premises, you may have local user accounts, you may have NIS, you may have LDAP. Now we have to go to AWS and see what are your alternatives there. In terms of scaling, you can look at alternatives where you want to, pre-provision an environment or scale on the fly. Then you have to do monitoring of the cost and see ways to optimize the cost on the cloud. Then you have to set up a proof of concept and validate your design. So whatever design option that you have chosen, you validate that design with a sample workload with a particular user group. And once that is validated, then you implement that design on the AWS cloud. So this is kind of a solution approach that we go through. And this is applicable not just for AWS, but for the other cloud providers as well. Similarly, if you look at Microsoft Azure again is the second leading cloud provider. And the difference between Microsoft Azure and AWS is that Microsoft Azure provides RDMA enabled instances. So you have InfiniBand enabled instances on Microsoft Azure. So if you have any kind of workloads that require RDMA communication, then Microsoft Azure can fulfill your requirements. And AWS has its own different kind of interconnect, but which is not RDMA. Again, just like AWS, Azure has a very wide range of compute as well as storage options. Like I mentioned here, they have RDMA enabled instances that are specifically suited for high performance computing. You have different kinds of storage that is available. You have object storage, you have file storage, and you have container storage. And this is extensible from the cloud to your on-premises environment. Just like AWS has its own scheduler and also supports different HPC schedulers, so does Microsoft Azure. It has its own batch scheduler. It has its own solution for deploying HPC clusters. It supports the Microsoft HPC pack, so you can create a Microsoft Windows cluster on Azure. And it also has a very wide range of data management and security options. So when it comes to identity and access management, all of the cloud providers meet the compliance and security standards that are mandated by, let's say, acts such as the Sarbanes-Oxley or GDPR. And if you want to do any post-processing and visualization, there are tools that are based on Citrix that are available for doing visualization of your output data. So Microsoft Azure also has a very large portfolio of compute and storage services. And one difference between AWS and Azure is that Azure has RDMA-based instances that are suitable for HPC design simulations that are used mostly in the automotive and aerospace and engineering simulation services in general. So now this is a sample architecture for an HPC deployment on Microsoft Azure. You can see here the solution is deployed using the Azure Cycle Cloud technology. Azure Cycle Cloud enables you to not only deploy compute clusters, but also storage clusters. So if you have a parallel file system like BGFS, you can create a storage cluster for BGFS using Azure Cycle Cloud technology. You can also create compute clusters which are based on schedulers such as Altair PBS Pro or IBM Spectrum LSF or Slum. And you can specify the number of compute nodes or the number of GPU nodes that you want to provision as part of your HPC cluster. So this is kind of a sample architecture for a compute cluster that is provisioned based on Slum and that uses BGFS as the parallel file system. So what the cloud providers do is simplify the provisioning and deployment of these kind of HPC infrastructure. So if you're designing an HPC infrastructure on premises, the provisioning of the HPC infrastructure may take you up to a week, whereas you can do this deployment in a couple of hours on the cloud because the tools are already there. The environment is tightly integrated with the tools. So this is an example of kind of a PaaS model where the platform of Cycle Cloud is there, and based on the Cycle Cloud platform, you can deploy your own HPC clusters and you can deploy your own simulation services on top of this HPC cluster. The third biggest cloud provider is Google Cloud. Again, Google Cloud has the same kind of components as AWS and Azure. So here again, you have specialized high performance resources that are available for high performance computing. They have their own specialized interconnect. If you require, you can also request InfiniBand for your Google Cloud environments, but they have their own low latency interconnects for their interprocess communication. Just like AWS and Microsoft Azure, they have a very wide range of CPU, GPU instances. And since Google was kind of the developer for TensorFlow and the AI frameworks, they also have tensor processing units. So if you have AI workloads, then the architecture or the infrastructure for the Google Cloud platform is optimized for those kind of workloads. So again, the storage instances are you know um, designed for different kinds of storage classes. So whether your data access is frequent, infrequent, or archival, you can request a particular kind of storage. Then you have a number of tools for bursting from your data center to your cloud environment. You have different uh, data lake services, so you can put different kinds of data, whether it is structured, unstructured, audio, video, binary data, all in a particular data lake. And there are different monitoring and visualization solutions available for post processing as well. So Google Cloud is also something that is coming up big in the HPC environment due to their wide range of processor and GPU solutions, and additionally their solutions for AI workloads. So due to the Google investment in TensorFlow, you know, TensorFlow runs very easily and gives you very high performance in the Google Cloud environment. So now we've looked at on-premises models and public cloud models separately. But like we mentioned, there may be certain requirements that may not be possible to fulfill on the cloud. So, and there are certain requirements which cannot be fulfilled on premises. So fast unlimited scaling is a requirement that is difficult to fulfill on premises, because procurement and configuration and provisioning may take a long time, which is much simpler on the public cloud. There may be a requirement to burst to cloud based on the business requirements of the workloads that you're running, in which case your existing on-premises environment may not be sufficient. You may have a very steep learning curve for new users of your HPC environment. You may need to tell them about what a scheduler is, what kind of instances to submit it to, which queue to submit it to, how to manage the data, how to archive the data, when to archive the data, and that may be something that may be very difficult for the end users. But you can have an HPC solution on top of your public cloud, which makes it very easy for the users. So the users can just come in, submit their jobs, and they don't have to worry about data management because the data space expands according to the usage. Or you can have lifetime policies set up on the data. So if the data is older than 6 months, you archive it. If the data is older than 2 years, you delete it. Or if the data is older than a month, you move it from SSDs to SATA disks. So you can do all of that on top of the cloud environment. And then it becomes very easy for the end user to come and use your HPC environment. It is also very difficult to upgrade your existing on-premises environment. While it is easy for the cloud providers to do it because they are operating at scale. So if you want to move from one processor version to a newer processor version, it is far easier to do that on the cloud environment because they are deploying it at scale. So you may get to test your workloads on Intel Broadwell, Intel Haswell, Skylake, and Cascade Lake. Or if you want to test your workload on the latest NVIDIA GPUs, you don't have to buy the GPUs because the GPUs are available on the public cloud. So you can just go to the public cloud, use those GPU instances, and then terminate them. So you only have to pay for the GPU instances that you've used. There is also a lot of security, regulatory, and compliance requirements around data. So if you are working in a life sciences domain, then you may have patient data, which you cannot transfer from one geography to another. So if your cloud environment is set up in Europe and your patient data is in North America, you may not be able to send it. So then you may have to keep the data on premises. Or you may have GDPR requirements in Europe, but you may not have GDPR requirements in, say, Asia. So, in that case, you cannot transfer data from one continent to the other. So you may have data silos. You may need to have data silos because you have to have compliance and regulatory requirements that you have to fulfill. So in that case, you need to still maintain your on-premises environment while you create a cloud environment for your other business needs. So due to these kind of requirements, we are seeing a growing trend towards hybrid environments. So a customer will retain an on-premises environment, but will have a public cloud environment or um, or a public cloud environment where they can run some workloads, where they can store some data, where they can test out new technologies or look at certain business requirements. So going forward, we are seeing a lot of trend toward hybrid cloud models, and the middleware and the software on top of that are evolving to make that possible. So as we come to the end of the session, I just wanted to give you our engagement with the academia. So TCS works with several different academic institutions across India, and we do a lot of work with these academic institutions. So, we support the daily forecast for weather forecast that are carried out at certain institutions here, such as IITM or um, IPR, or SAC. We can provide support for those kind of daily weather forecast. Our environment was used by ISRO. The Tata supercomputer was used by ISRO for CFD simulations of launch vehicles. We have participated in aerodynamic analysis of regional transport aircraft. We have provided stable and tailored HPC environments to researchers and students. We have helped different universities and different research organizations optimize their HPC environments. We have worked with them to develop custom accelerators for workloads, and we've also deployed data security mechanisms at their installations. So we are engaged with different kinds of organizations in academia and research on all aspects of the HPC life cycle. So we have come to the end of the session. This is my email address. I think it would be better if you were to route your queries through Dr. Sushil. I think it would be easier for me to address those queries that way. I will be sharing this presentation with you, so you can take a look at this in your time. And if you have any follow-up questions, you are free to send me an email. Okay. I'm just going to address one question here from Sham. If I want to gather the metrics of nodes and as well as job while it is processing, which open source tool should be used, like CPU time, usage data locality, etc. Uh, if you can go on mute, I will address these questions. I think somebody speaking.
Hello.
Yeah.
Hello. I am Rajesh Dharmik, Head Department of Information Technology.
Yeah.
On the behalf of Department of IT, I would like to thank Saurabh Barve sir for your nice presentation on high performance computing on cloud technology. Suppose you are talking about cloud or cluster or grid computing, in which the high performance computing is involved. And nowadays, most of the scientific institutions are working on HPC, like CDAC or Baba Atomic Research Center. So they have their own high performance computing infrastructure, right? And you have nicely presented all these concepts and content on HPC. So it is definitely useful for our faculty members as well as all the participants. And again, this is my humble request to all the faculty members to incorporate these contents as far as the usefulness of student is concerned. Again, we are getting some expertise from the industry people, and the content is also useful for how to involve that content into our curriculum. So again, this is very much useful for us. Anybody have any queries or questions, please ask you Barvesh.
Yes, thanks. Thanks for the kind words, Rajesh. It was a pleasure to present the industry perspective to an academic and research audience. So Sham, I have addressed your question in the chat window. These are some of the tools, open source tools that you can use. There are a number of other tools, but these are the most popular tools and very mature tools that you can use.
Saurabh sir, I'm also thanks to TCS for provided us an excellent sticker for our FDP program.
Sure. Thank you. Thanks for the kind words. Yes.
Okay, thank you, sir. Thank you.
Okay, so I'll wait for another couple of minutes. If there are any and there are any further questions, you can ask over audio, or you can type in the chat window.
Yeah.
Okay. Okay, so I think Sham needs to be unmuted. I think you can unmute yourself, Sham. I don't know. Okay. Yeah, so Sham, I think that is kind of the development that goes into HPC solutions. You mentioned about problems with time series analysis. So that is something that, of course, we encounter when you're trying to solve an industry specific problem. But I think if you, I think Google it. If you have any specific problems that you face, I can guide you to certain solutions that are already there. If you have any specific questions with regards to technology, and if those are easily addressable, I can address them over email. Sham, you are unmuted, so okay. We can interact over email.
Hello, am I audible, sir?
Yes.
Okay, great. Thank you. Actually, I was working with a Spark and I was trying to run the job on the Spark. And then Spark history, I had actually tried to gather the metrics related executor CPU time, executor CPU memory usage, and like IO, as well as how much amount of time each job takes. And then I was trying to predict the next job, the similar type of job when it is about to run in the next time. So that much I did, but only thing is that when I was trying to run the Spark, trying to collect it, I was trying to collect it using Ganglia. At that time, the timestamp which it provides me, I cannot club these two, metrics together. The CPU time at that particular time instance used by the Spark and the CPU time which is being captured by the Ganglia at that time instance. These two cannot, because job ID and task ID, executor ID, these are the things which are totally different. And then I have to merge these two data sets. But due to timestamp issue, I will not able to guarantee that at what time instance that particular job has taken how much amount of CPU. That is what actually I was trying to.
Yes. So HPC schedulers actually do provide you with
Yeah.
job-wise utilization. So a
Okay.
scheduler like Altair PBS Pro or IBM Spectrum Scale LSF will provide you the compute utilization per job.
Okay.
There is also accounting information that is collected by schedulers, which can be extracted out from the scheduler logs, and then you can look at the CPU utilization across nodes for a particular job.
But will I
So
get
on
the timestamp also including?
yes, you can also get the timestamp. You will,
Because
yeah. So if you are
Because
collecting any,
In Spark log, I did not get any timestamp. I get only execution start time of a particular task and the end time of the particular task, finish time. These two things
right,
only I get in the Spark history log. But I don't get at every moment how much time, I mean, kind of a task progress I wanted. Because log I get only after the execution of the job. But while that job is running, if I can capture the task progress, and I can say that this task is getting slow, okay, then that is what it is, my actually aim is to predict that this task is going to get slow. So early warning system kind of a thing.
correct. So generally, I think that is something that you would have encountered, that one single tool may not be able to do all of what you want. So you may
Okay.
need to combine different tools. You
Mhm.
may get processor information utilization from Ganglia. You may need job-wise utilization from an HPC scheduler, start
Mhm.
times, end times for the Spark job through the HPC scheduler. Combine them, use some visualization tool, maybe store that data in a database for easy access. So
Mhm.
you may need to experiment with different tools
Right,
um,
sir. Mhm.
to have that particular solution for your particular problem.
Yes, sir. I tried that. Only thing which I could not able to address is like while that job is running and it about to get slow because of some resources having some issue. So like the task progress getting slow in between, just like a speculation which we do in the Spark. Speculative execution, it happens and it checks while the task is in progress. So it checks that how much amount of time that task is taking to complete. Okay, and it will try to predict that okay, this particular task on this particular machine is taking more time than the expected one. So it tries and shift that particular task on some another machine which is faster than that. So that is a speculative analysis which is being done, but while job is running at that time. But I could not get into it because the Spark is like it's a huge code, and I could not able to hook into that particular, like you can say, that area where I can basically continuously monitor the task progress. Externally, I cannot do by either by using any monitoring tool. It is being done in the heartbeat message, and that heartbeat message modifying that and reconstructing that is getting a lot of issue. Like I could not able to do it.
Okay. Um, I don't know if I'll be able to solve your particular query right now,
Yes.
but
Yeah.
that is the kind of research work that we do in our center of excellence. Um, not just solution design in terms of industry, but also application optimization, application porting,
Yes.
and
Yes.
these workflows that you mentioned, or predictive or speculation of
Yes.
job failures. That is the kind of work that we do. I think
Yes.
if you would like, I can connect you with people who have done research on that, and they may be
It
able
will
to
be
give
really
you
helpful, sir.
that
Thank you, sir.
particular
Yeah.
information.
Yes,
Yeah.
sir. Yes. Thank you very much. I'll send you a mail, sir, regarding the work which I am doing. I have a few papers, so if you can just go through and let me guide on, like this is where the one of the actually work which I would like to continue with. That I wanted to basically have, wanted to predict while that job is running online, like at that time itself, rather than taking its metrics afterwards and then doing it offline and then providing it so to a predictive scheduler, a kind of a predictive scheduler. So rather than that, if it is online scheduler, which will immediately being warned that okay, this is the particular node which is deteriorating your task. I mean, sorry, deteriorating the performance. So immediately can we predict that it will not it should not schedule the next task onto it.
Right, but to train your tool, you will need
Yeah.
to train it on offline data.
Huh. But then the start time and the finish time, these are the only two things which I get from the Spark.
Okay.
And then the progress pattern, I will not be able to feed it to the machine learning algorithm. That
Okay.
progress pattern is very much important for me. At time T1 to Tn, what is happening, how it is, if it tries and see that pattern in the particular current task which is running on that particular machine, so immediately it will shift before, either it will avoid that node next time or it will try and shift immediately before speculation itself, like task progress itself.
Okay. Um,
That's it.
well,
Yes.
I was thinking whether it would be good for all the participants, if you have queries, to forward them to Dr. Sushil, who can then
Yes.
send it to me. Instead of everybody individually sending it, I think that would be better because the volume of email that we deal with is quite significant. So we may miss certain queries.
Yes. Thank you, sir. Sir, you
Uh,
can mute me.
Thank
Yeah.
you, Shan.
Yeah.
Hello. Thank you, Shan, for your question. I think so. You got answer for your query. And
Yes, sir.
again, apart from this, suppose you have any doubt, simply post us, and we will convey to our experts. Right?
Thank you,
Right.
sir.
If there are no any queries from any other participant, then I will conclude today's session. Thank you all the participants for nice patiently you are attending all these three sessions. And tomorrow session will start at morning 10 o'clock. Right? Okay, thank you one and all, and thank you, Saurabh.
Thank you. Thank you very much.
Thank you. Thank you. Thank you.
थांबा थांबा आपण बघूया